In this video, we are going to learn about four very common circuits inside of our computers. And they perform two branches of functionality for us. The first two provide one branch, and it's called decoding and encoding. And the second one is multiplexing and demultiplexing. And these circuits are extremely common, so we're going to look at what they do abstractly, how they work internally, and talk a bit about what they can be used for. And in both cases, both of our branches have the capability to be used, which is pretty neat, to make any arbitrary circuit at all. So let's get started with these. Now, the first thing we're going to talk about is decoding. And a decoder is a little circuit that we draw abstractly like this. It has some number of inputs. In this case, it has two inputs. And it converts from two inputs to four outputs. Now, all decoders are not two inputs and four outputs, but if they have n inputs, they will have 2 to the n outputs. And the way they work is effectively that they take the inputs as if they were a multi-bit unsigned value. So in this case, we have a 2-bit number. And that means it could be a number between 0 and 3. And what it produces for output on its output lines, which are coincidentally numbered 0 through 3, is if you put in the 2-bit number for 1, for example, 0, 1, then what's going to happen is all of these wires are going to have a 0 coming out for it, except the line associated with the number 1. So if your input is the 2-bit number for 1, output line 1 is going to go high, and all the other lines are guaranteed to be low. In fact, you'll always have one and only one output line high with a decoder. Now, you could also have a decoder with 3 inputs. You can give it a 3-input number, and since 2 to the 3rd power is 8, any such decoder is going to be a 3 to 8 decoder. So 3 lines of input, 8 lines of output numbered 0 through 7. And the same basic rule applies. So if we provide the 3-digit number 44, line 4 coming out is going to be high, and all the other lines are going to be low. There will always, however, be some line high because there's always some value, 0 or 1, on all of these inputs. So we're always going to have one and only one output wire high on a decoder. So let's take a look at how the internals of these work. And this is actually going to reflect a pattern that we've already seen when we've been doing digital logic from the sum of products forms expressions. So here is the 2 to 4 decoders internals. Our two inputs, A1 and A0, are bussed down. And then realistically, this is 4 separate circuits, right? So here is the output for line 0 associated with this. Here's an AND gate for output for line 1, 2, and 3. Each of them are just a single AND gate. And if you'll recall this notion of a little character standing right here with the head up here, leaning over to the left so that you're reading these from bottom to top, that'll look like it's from left to right. Each of these AND gates have what appears to be numbers like 1, 1, 1, 0, 0, 1, and 0, 0. And each of those are the 2-bit patterns, 2-bit input, 2-bit patterns for their respective output. So 3 is 1, 1, so this looks like 1, 1 when we turn our head this way. 2 is 1, 0, 1 is 0, 1, and 0 is 0, 0. And I'll remind you of how this works functionally. So if we wanted line 0 to go off, and we put in the bit pattern for 0, which is 0, 0, each of those inputs of 0 would come to these inverter bubbles and be turned into 1s. And then you'd have all the 1s of this AND gate, all the 1s of the input of this AND gate, all the inputs of this AND gate being 1s, and our output would be 1. But that guarantees, because all these others don't have exactly that same input pattern, that these will all have at least 1 0 for input and produce 0 as output. You can follow through on each of the others to see that this is the case. And this scales very trivially. So if we wanted to look at the 3 to 8 decoder, here we would have 3 inputs bussed down, and then 8 AND gates, one for each of the outputs. And then if you just stand here and turn your head over to the left, you can read the bit patterns right here at the input line that appear to be, or that appear as bit patterns, and they're the same as the number they represent. So the output for 5, this looks like a 1, 0, 1, which is 5. 3 is 0, 1, 1, that's 3. 0 is 0, 0, 0. So decoding is a very simple process, but it allows us to take a compressed value like a 2-bit number or a 3-bit number or more, and then reconfigure it, so to speak, so that what we're really doing is taking and bringing some associated line high and leaving everything else low. Now these are used for all kinds of things. We're going to get to some stuff in a little while that's a little bit universal, but one of the common uses of a decoder is we can put some kind of a counter up here in front of the input. So let's say we have a 2-bit to 4-bit decoder. We could put a counter up here, and then when our computer system turns on, we could run through a bunch of system startup checks before we get to the main processing program of our little system. So for example, that counter could start with the value 00 in it, and so this wire here would fire off, and that could be connected to some circuit that enables the initial memory test. And as soon as the memory test circuit completes, it could send a signal back to our counter so that it increments and goes from 0 to 1. Then we would suddenly fire off subsystem 1. It would run off to some circuit that does some next stage startup, like it loads preliminary data from the firmware, something like that, all the way until we get to 3, which might just do a raw execution of our system from here on because we're already booted. So decoders are very useful. Now the opposite side of decoding, since decoding takes a multi-bit number and expands it decodes it into which specific number it is, we want to be able to do the alternate, and that's called encoding. So with encoding, here is, we're only going to show one, but this is the opposite of the 2 to 4 decoder. We'll have a 4 to 2 encoder. Here we have 4 pins of input, inputs 3 through 0. And unlike the decoders where these values could be anything, there's got to be something controlling the signals that come to here so that we can guarantee that one and only one of its inputs are high. But there's always at least one of them high. If none of them are high, or some other combination is going on, then traditionally we would just say the behavior of this is undefined. And so that allows us to make one that does something special with that unique situation, or whatever we might decide. So we take each of these 4 inputs and we might say, well, A2 is high and all the other pins are low. Well, then what we're going to produce as output is a 2-bit number, high order bit, low order bit, a 2-bit number for the number 2. So if we had A2 high and all the others were low, then we would get for x1 a 1 and for x0 a 0, because 1, 0 is the binary for 2. If we made A3 go high and made the rest go low, then we would get a 1 on both x1 and x sub 0. So what we're going to do quickly is derive the circuit for this on our own. So I've got a 4-input truth table here because I have 4 inputs to my circuit, and I have 2 separate outputs because really this is 2 different circuits. Each individual pin coming out is a unique circuit, has a unique circuit behind it. So how does this work? Well, A3 could be a 1, and each of these could be zeros. A2 could be a 1, and the others are zeros. A1 could be 1, and the others are zeros. Or A0 could be a 1, and the others are zeros. Now, you might be saying, well, this is a 4-input circuit. Shouldn't we have 16 minterm rows? Well, we could. We could write all of those out, but the behavior for all but these 4 are effectively undefined. So since some other circuit in front of this thing is going to guarantee that these are the only possible input scenarios, we're just going to work directly off of this. So how does this work? Well, if A3 is high, then the 2-bit pattern that comes out is the number 3, 1, 1. A2 goes high, it's the number 2. A1 goes high, it'll look like the number 1, and if A0 goes high, it'll look like the number 0. But from this, we can very easily derive the circuit, because if we consider x sub 1, when does it have a 1 versus a 0? Well, it has a 1 when A3 is 1 or A2 is 1. So that will look like this. We'll have an OR gate for x sub 1, and it's going to go high whenever A2 or A3 is a 1. So we'll just make our connections directly to A2. No inversion bubble so that a 1 comes right in. And then another one for A3. No inversion bubble. Very similar to what we did over here. We're going to take a 1 on either one of those. And if either is a 1, then that'll make the output of this a 1. And if both of them are 0, then this will turn out to be 0. Right here, as we see in our truth table. Now x sub 0 is a little different. 1, 0, 1, 0. So it's 1 here and 1 there. That's on A1 and A3. So another OR gate whenever A1 is high or A3 is high. Now, this is actually, each of these two circuits, a sum of products form expression realized in its circuit. It's just that the product, like in this case, A1, has only one term, so we don't really see anything being ANDed with A1. But you might as well think of this as A1 ANDed with 1, or A3 ANDed with 1, right? And so it's the same kind of circuit that we've actually seen before, and we can very quickly derive and create an encoder circuit. And these, additionally, like the decoders, scale very easily. Now, a fun thing about the decoder is that we can use a decoder to make any circuit at all. And the way this works is we think about, if you think about the sum of products min-term form expressions, these give us a nice shorthand to indicate which output rows of a truth table for a particular function are going to produce a 1. And if any of the min-term input patterns show up as the input, then one of those min-terms in the sum of products min-terms form expression, one of those rows is going to be what's happening, and so we're going to get a 1 as output if we consider it from a decoder perspective, right? So in this case, I've got some circuit I just made up, Z, that has a 1 on 1, 2, 4, and 5, right? So if I put A, B, and C here as the inputs, then I get my 3-bit numbers coming in, and they'll be decoded such that whichever number it represents, that numbered wire output becomes a 1, and everything else becomes a 0. So if, in this case, 1, 2, 4, or 5 turn out to be high, I want a 1 to come out of my circuit in general. So what I can do is just OR those outputs together. I'll put a nice big OR gate here. Say that's circuit Z, and I'll connect it to 1, to 2, to 4, and to 5. Now I don't even need to connect the other outputs from the decoder, because if the 3-bit input in this case turns out to be the bit pattern for a number other than 1, 2, 4, and 5, then 1, 2, 4, and 5, along with most of the rest of the wires, will have zeros. And so zeros going into the OR gate is going to produce a 0 as output, which means the larger circuit Z is producing a 0 as output. So let's do the same thing for this other function that I made up, which I also called Z. But this is a 4-input function with A, B, C, and D as inputs, and it produces high output on 3, 5, 7, 8, and 12, and 0 in every other circumstance. So we can complete converting this decoder into our universal circuit generator for Z very easily. We just add an OR gate. This one a little bigger. Then I start connecting it. 3, 5, 7, 8, and 12. And there we have it. With a decoder and an OR gate, we can very easily produce a circuit that performs any logical function we like. All right, so let's now move on to talking about multiplexing and demultiplexing. And we'll start with multiplexing. So, do you remember this little cutie? He's the transistor. Now, the way that transistor worked, if you'll recall, was a lot like a telegraph switch. So think about that thing where you press the button down and you've got a wire over here at this elbow and another wire over here. And when they're disconnected, the signal that comes in on the collector side does not make it out the emitter side. But when the telegraph switch is pressed down, whatever signal is coming in on this end is going to go out on that end, right? So the transistor conceptually is a simple thing. The same thing is true, though, for the AND gate. If we take a second and produce the truth table for what our binary kind of transistor is going to do, you'll notice that we have the collector pin, which can get routed to the emitter pin only if the basis pin is high. Under all of the circumstances, the emitter is just going to put out 0. And so the data coming in on C is not routed through this little gate. So over here, the truth table then, if we draw the whole thing out, when the basis pin is 0, which I've underlined in red, then the output is just plain 0. And it's 0 because of the basis pin. We don't even bother to look at what's coming in on the collector. However, if the basis pin is high in the bottom half of this table, then the output is determined by whatever value is in C. Effectively, C is being pumped out. But if we look at the output column, the output midterms go 0, 0, 0, 1. That's the same as an AND gate, which means we can perform the function of that telegraph switching, gating system for data digitally with an AND gate. And that might seem ludicrous if we could just do it with a transistor, but if we're building circuits out of logic gates, we're not really building them directly out of transistors. So we have to think about how these circuits work through digital logic, not necessarily transistors. But we can see how they work abstractly in the same way. So here we have the basis pin coming into this AND gate, the data pin C coming into the AND gate, and if that basis pin is high, then the value on C is going to come out on the emitter side. So here's how multiplexing works then. It's going to rely on this concept in the end. A multiplexer is often drawn as this sideways trapezoid, and the data comes in on the big side and comes out on the little side. And you could think of this like some Arnold Schwarzenegger Running Man scenario, like many come in, only one comes out. Right? Think about it that way, you'll remember what a multiplexer is. So we could have, say, 2 things coming into the multiplexer, and then 1 will come out. We could have 4 things coming into the multiplexer, and 1 will come out. We could have 8 coming in, 1 will come out. It'll almost always be a power of 2 inputs, but it'll always be 1 as output. What is different between the number of inputs and the single output is how many control lines we have. So like the decoder, we had these inputs that were a multi-bit number. We've got the same thing here. So this is just a 2MUX, what we call it, which means it has 2 inputs. And to distinguish between which of these inputs we want to route to the output, then we put a value here on this control pin. So if this one wire has a 0, we'll pick 0. If this one wire has a 1 on it, we'll pick input 1 and route it out on X. So we can make that circuit really easily by duplicating this transistor-ish gate concept over here with the AND logic. So we can take a 1 to 2 decoder, run our control line into it, and so if we bring in a 0, output line 0 will go high and output line 1 will go low. If we send a 1 in, 1 will go high and 0 will go low. But one and only one of those is going to go high, and that means one of these 2 AND gates is going to have a wire from the decoder that's high, which will allow it, as the basis pin, to let the other line of data coming into that AND gate pass through to the emitter. And those are our data inputs, D sub 0, D sub 1, just like this diagram over here. So if we put in a 0 for our input up here on the control, then whatever is down here on data 0 is going to come in, whether it's a 0 or a 1, it's going to get passed on through to this OR gate. Now, we don't have to worry about what the other guy is doing because he's guaranteed to produce a 0. If x sub 0 is 1, x sub 1 is definitely 0. So we're going to get 0 coming out, and 0 ORed with anything is the other thing. And that'll give us our multiplexed output. It's a fairly simplistic circuit built on top of a decoder and using AND gates pushed into an OR gate. Now remember also that this looks familiar, right? A row or a column of AND gates, all of whose output go into an OR gate. That's like our sum of products form realized in digital logic. So this is all something we should be very familiar with. Now let's look at a bigger multiplexer, a 4 MUX. We would draw this in our circuits like this because nobody cares about all this internal stuff. As long as we know how a MUX works, we can just do something like this. So if we're going to have 4 data inputs, we're going to need 2 control lines to pick from the 4 inputs. And that's going to just be a direct scaled expansion of the 2 MUX. So we got a 2 to 4 decoder. Each of their outputs run as a gating input to an AND gate. And then the other line to each AND gate is just the associated data line. One and only one of these AND gates will be allowed to pass a 1 through. And so if that data line has a 1 on it, it'll get routed out to the OR gate and passed out as the output of the multiplexer. Now, similarly to the decoder, we can actually use a multiplexer to make any arbitrary circuit we like as well. So we're going to take a quick second and look at this particular function I've written here in the sum of products midterm form. And then we'll generate a working digital logic circuit for it using just a multiplexer. So the way we do this, remember this is a situation where for 3 inputs, A, B, and C, we're going to produce a 1 as output if that 3-bit pattern is either the numbers 0, 2, 3, 5, or 6. So the ABC come in as control lines to the multiplexer. A, B, C. And they're going to pick which of our 8 inputs, 0 through 7, are going to get routed to the output. So whenever these represent one of these numbers, which will be associated with the same numbered inputs, we want a 1 to come out. How do we get a 1 out? Well, we just hook it up to power. So I'll just take a bus from power, and here's our power symbol up there. And I'll say that on 0, I want to route, on the 3-bit pattern for 0, I want to route whatever's coming in on line 0 to the output. Well, power is getting routed to the output, so that's high voltage, and we've got a 1. I'll do the same for 2, same for 3, the same for 5, and the same for 6. But unlike when we did this with a decoder, we can't leave the other ones disconnected, because then if somebody were to put in the 3-bit pattern for 4, we just have this sort of loose wire, and we could get who knows what kind of nonsense coming in as output. So we need to force a 0 to go there. We're going to do similar to what we did here. We'll just grab a bus that goes to ground, and then we'll connect those ground wires, which work as a digital 0, directly to the remaining inputs. So ground functions as 0, power functions as 1, and we just route ground or power to the output of this circuit, and now we've very quickly created a working circuit for this arbitrary function C. But if you think about it, effectively this multiplexer is no more than the decoder with an extra AND gate to pick from to gate data going into an OR gate. That's very much like the universal circuit generator we had with a decoder where the outputs of the decoder went into an OR gate. It's just that we have extra data lines, so they need the other AND gates to grab the signals from input. So this is a fairly simple circuit, but is all over the place in the computer. Now, one of the most common places that we'll see a multiplexing circuit is when we need to get, well, exactly what it's for. When you have lots of different things coming in, like inside of the CPU and the arithmetic logic unit, as an example, all the different types of mathematics will be being calculated potentially in a real simplistic ALU. So you could have addition and subtraction, multiplication and division. You could have them being all calculated simultaneously, and then a 2-bit control number will say which operation did we want to perform, like subtraction, for example. And then whichever one of these input lines has the result of the subtraction, that would get routed to the output. And if we did multiplication, a different line would get routed. Another thing that we can use this for is over long buses, say multi-device serial buses or something like that. So we might give a little bit of time to device 0, a little bit of time to device 1, a little bit of time to device 2 and 3, and their bits would come out in kind of a stream over that multiplexer, something from each one after another. And if there was a counter hooked up to this and a clock, then it'd go device 0, device 1, device 2, device 3, device 0, device 1, 2, 3, and so on. So we'd have a pattern of inputs coming from one end. And as long as we had the opposite of multiplexing on the other side, connected to somehow or another to the synchronized clock that was moving this counter, then the other side of this thing would always know which of the 4 output devices to route it to. And that's what demultiplexing is. So in demultiplexing, we have a data line and the same number of control lines as we might have had on the multiplexing side, and we just route the data out to one of these different output lines. So if we're thinking about one of 4 devices getting multiplexed to a single wire coming over here, and it says in these input numbers that this is device 2, then it'll be a 1, 0, then the data that's coming in right now will get routed to output 2. So how do we build a circuit for this one? Well, this one's actually very simple too, and it again reflects the pattern that we have seen over and over, this column of AND gates. So we've got 4 individual outputs, which really means 4 individual circuits. Each of them function off of an AND gate. And the AND gate is going to work like the transistor in this case, where it's just allowing data to go through, but it needs the basis pin, and that's going to come from the output of our decoder. So each AND gate connects one of its 2 inputs back to the decoder, so that when a particular 2-bit number comes in this case, because I'm doing a 4 DMUX, which means I have 2 control inputs, then let's say that's the number 2, then this wire is going to go high and come out to here. Now these are going to have their individual outputs, and this will be x sub 0, x sub 1, x sub 2, and x sub 3. But then there is this data wire coming in. So I'm going to run that data wire right into this AND gate. So far this is starting to look like a multiplexer. But what's going to happen that's different is I won't put an OR gate back here. And instead of having a bunch of different data inputs, data sub 0, data sub 1, data sub 2, data sub 3, I'm just going to copy that same input all the way down to each of these AND gates. So the data is being routed to all of them simultaneously, but the data doesn't make it through the AND gate unless the associated output line of the decoder is high. So there you have it. We've covered 4 types of circuits from 2 families of activities. We've done decoding and its counterpart encoding, and we've looked at multiplexing and demultiplexing. We've also looked at how we can use a decoder or a multiplexer to produce an arbitrary circuit trivially.